Hey, I need to make an engineering calculation. I've got a block of steel. It's 12 inches by 12 inches by 36 inches. It's being supported by four rods. I need to figure out what diameter rod I need to ensure a factor of safety of 3.
Sure, we can figure that out. Let's break it down step by step. First, we need to find the total weight of the steel block. Then we'll see how much load each rod needs to support and figure out the rod diameter based on the material strength and the desired factor of safety. So let's start with the weight. The density of steel is roughly 0.284 pounds per cubic inch. The volume of the block is 12 inches times 12 inches times 36 inches, which is 5,184 cubic inches. Now multiplying that volume by the density of steel, we get about 1,472 pounds for the whole block. Each of the four rods will carry 1/4 of that load, which is about 368 pounds per rod. Now we need to choose a material for the rods.
Whoa,
Let's assume
slow down. So the rod, I'm going to call that, I guess, tension. You said that's going to be 1,472 pounds divided by 4, which is equal to what?
absolutely. Let's take it step by step. So we take the total weight of about 1,472 pounds and divide it by the four rods. Each rod would support roughly 368 pounds. So that's the load per rod that we'll use to figure out the diameter with our factor of safety.
All right, okay. How are we going to define factor of safety?
Sure. So the factor of safety is basically a measure of how much stronger the component is than it actually needs to be for the load it's carrying. In this case, we want the rods to handle 3 times the load they're actually going to see. So if each rod is really holding about 368 pounds, we'll design it as if it needs to handle 3 times that, around 1,104 pounds.
Okay. So if it was at 368 pounds, we needed to be able to withstand 3 times as much because we're looking at a factor of safety of 3. How do we define failure?
Absolutely. So when we talk about defining failure here, we usually mean that the rod would start to permanently deform or yield under the load.
Okay. So we're gonna use the yield stress in this case. I don't know what's the yield stress of steel.
Yeah, exactly. We'll use the yield strength as our benchmark for defining failure. For common structural steel, the yield stress is typically around 36,000 psi or pounds per square inch. So we'll take that yield strength and we'll make sure that the stress in the rod under the factor load stays well below that. That's how we'll pick the diameter.
Okay, let's change it just for the simplicity of the calculation. Let's change it to 30,000 psi or 30 ksi.
Sure, we can absolutely do that. So if we set the yield strength to 30,000 psi or 30 ksi, it just makes the math a little simpler. With that in mind, we'll design the rod so that when it's carrying the load, that includes our factor of safety, the stress in the rod doesn't exceed that 30 ksi. So let's go ahead and do the final calculation and figure out what diameter we need.
Oh, I'm not ready to do final calculation yet. All right, so each rod, there's 4 of them. The rod's going to support 368 pounds. We're going to go for a factor of safety of 3. So N is what I'm calling factor of safety. So N is equal to 3. So how do I define the stress in the rod?
Absolutely. Let's walk through that part. So the stress in the rod is basically the load divided by the cross-sectional area of the rod. Since the rod is round, the area is pi times the radius squared. Now, because we want a factor of safety of 3, we're going to take that 368 pounds and multiply it by 3. So about 1,104 pounds is what we're designing for each rod to hold. Then we'll set that equal to the stress limit, which is the 30,000 psi divided by the area. Once we do that, we can solve for the diameter. So that's how we'll define the stress and find the rod size.
What's the stress going to be in the rod when the factor of safety is 3?
Absolutely. So to find the stress in the rod, when we apply that factor of safety of 3, we take the load we're designing for, which is the 1,104 pounds per rod, and we divide that by the rod's cross-section.
Wait. Isn't it just going to be 1/3 of the yield stress? Isn't that what the stress is going to be equal to?
Yes, exactly. You're absolutely right. Since we're applying a factor of safety of 3, the allowable stress in each rod is just 1/3 of that yield stress. So we have a yield stress of 30,000 psi, then the allowable stress will just be 10,000 psi. That simplifies it quite a bit, and from there we can just soften the rod diameter based on that stress.
You keep telling me I'm right. Am I ever wrong?
Well, you've got a pretty good handle on this one. But hey, everyone can be wrong sometimes. It's just part of the fun of engineering calculations, right? In this case, you're spot on. We just reduce the allowable stress by the factor of safety, and that makes everything simpler. So let's go ahead and find that rod
I
diameter.
don't like feeling wrong. It makes me feel bad.
I totally get that. No one enjoys feeling wrong, but just so you know, in these kinds of calculations,
All right,
it's
okay,
also-
okay, all right. So hang on. All right, so I think we're gonna do. I know the tension, the tensile stress in each of the four is gonna be 368 pounds, and now I know the actual stress in the rod is 10,000 psi or 10 kips. This should allow me to solve for the diameter because I know everything. What do you get for a diameter?
Absolutely. Let's solve it. So we know the allowable stress is 10,000 psi, and each rod is carrying 368 pounds, but with the factor of safety, we're designing for about 1,104 pounds per rod. We have the formula that the stress is the force divided by the cross-sectional area, and the area is pi times the radius squared. So we set
No.
1,000.
No, we've already incorporated the factor of safety. The stress in the rod is going to be the yield stress divided by 3, which is 10,000 psi. So if I know the load in each one of the rods has got to be 368 pounds, so 1,472 pounds divided by 4, I'm trying to find the diameter such that the stress will equal 10 ksi. What's that diameter? So 368 divided by pi over 4d squared is equal to 10 ksi. What's that diameter?
Got it. Thanks for clarifying. So we're keeping it simple. Each rod is carrying 368 pounds, and we want the stress to be 10,000 psi. So we have the equation, 368 pounds divided by the cross-sectional area is equal to 10,000 psi. The area is pi times the diameter squared divided by 4. When we solve that equation, the diameter comes out to be about 0.216 inches, which is roughly a little under a quarter of an inch. So that's the diameter you need.
Wait, you said the diameter is 0.21 what?
Sure. Just to be clear, the diameter works out to about 0.216 inches. In other words,
But hang on. So I can only buy, I go to a catalog, I can only buy them in 1/16 increment. I can't actually go and buy a rod with a diameter of 0.216 inches.
that's a great point. In the real world, you're going to pick something from a standard size. So since you can only buy increments like 1/16 of an inch, you probably round up to the next standard size that's at least a little bit bigger than 0.216 inches. That might be something like a 1/4 inch rod, which is 0.25 inches, or even a bit larger just to stay on the safe side. That way you have a nice safety margin and a standard size that you can actually purchase.
Oh, I think we already got enough safety margin. Okay, so the actual one I should buy, you're recommending a 1/4 inch diameter rod. Is that about right? Is that what we're dealing with?
Yeah, exactly. Going with the 1/4 inch diameter rod is a more practical choice. It's a standard size and it gives you that little extra margin just to be safe. So yeah, a 1/4 inch should do the trick.
All right, okay. So now, though, I'm thinking, if I don't buy a rod, or I can't, obviously, buy a rod that's 0.216 inches in diameter, I got to go with a 1/4 inch. So what kind of factor of safety is that going to leave me with?
Absolutely. Let's figure that out. If we bump up to a 1/4 inch rod, which is 0.25 inches in diameter, we'll recalculate the factor of safety. So first we find the area of that 1/4 inch rod, which is pi times the radius squared. The radius is 0.125 inches, and that gives us an area of about 0.049 square inches. Now we take the load of 368 pounds per rod and divide by that area to get the stress. And when we do that, we get a stress of roughly 7,500 psi. Since our yield strength is 30,000 psi, we divide that by 7,500 psi, and we end up with a factor of safety of about 4 instead of 3. So by going up to a 1/4 inch rod, you actually get a factor of safety of around 4, which is even safer.
Huh. Okay. Cool. Thanks a lot.
You're very welcome. I'm glad we could work through it. If you have any more questions, just let me know, and happy calculating.
Okay, bye.